Welcome all for this lecture on Principles of Measurement. Myself Jenitha, Assistant Professor of EEE Department, and today's session we are going to cover the topics of what is measurement and instrumentation, and the block diagram of the instrumentation, errors in instrumentation, static and dynamic characteristics of instrument, essential requirement of an indicating instrument. So measurements are used in our day-to-day life, and it is used for measuring more physical parameters and electrical signals, and it is used in various fields. So what is, if we define the measurement, so measurement is an act or the result of quantitative comparison between an unknown magnitude and the predefined standard. So this is we are going to compare with the unknown quantity, the standard unit. So this is used in various fields including science, engineering and day-to-day life activities. So what is instruments? So instrument is a device that is used for measuring the values or magnitude of the quantity to be measured. So this is a device specially designed to detect, indicate or record the magnitude of a physical quantity. So example, there are many instruments. Here we are discussing about thermometers and rulers. These are the example for the instruments. And now we can see the block diagram of the instrument. So if we see this block diagram, here there are the block diagram of the instrument consists of the three stages. So first stage is a primary sensing element, and next stage is a signal conditioning or data conditioning, and the third stage is a data presentation. So this block diagram is classified into three categories. So the physical quantity to be measured is called as measurand. So this can be of anything. For example, it can be of any very physical parameters like pressure, temperature, velocity, etc. Or any other electrical parameters like voltage, current, etc. So the quantity to be measured is called as a measurand. So the quantity to be measured we are considering in the initial stage. So this comes under the primary sensing element. So what is primary sensing element? The first detection of the measurement is done by this primary sensing element. So if we consider the ammeter, so example of ammeter, we can consider the example of ammeter. So in ammeter, a coil carrying the current will be the primary sensing element. So if there is a physical parameters like the temperature or any temperature or pressure, etc. So first of all, first stage you have to convert it to the electrical parameters. So that we can done with the help of transducer. By transducer, we are converting the non-electrical parameter to the electrical parameter. So if it is an electrical parameter, we are going for the next stage, that is variable conversion. So what is variable conversion? It is the output of the physical sensing element is in the electrical form, and it should be adapted to the next stage. It should be the output should be accepted by the next stage. So if it is not accepted to the next stage, we have to go for the variable conversion. So in this conversion, we will be converting the parameters to the desired output form. So such as voltage, frequency or any other electrical parameter. So such output may not be in the suitable form for the actual measurement. So we have to go for the variable conversion. So for example, if the measurement system is in a digital, then if the output is in the form of analog, we should convert it to the digital form. So by this, in this variable conversion, we are going to convert the analog to the digital using the analog to digital converter. So in this variable conversion, we are able to convert it to the digital conversion. So next is so it is a sensing element stage, and next is a signal conditioning. Here we are going to manipulate the signal, or you are going to adjust the output to the desired form for the next stage. So what is variable manipulation means? The level of the output from the previous stage, that is, may not be enough to drive the next stage. So this variable manipulation element manipulates the signal and preserving the original nature of the signal. So for example, if we want to amplify the signal, then we have the magnitude of the input to be increased. So for that we are using the by the amplifier we can able to amplify the magnitude of the input and by retaining the original nature of the signal. So in some cases the level of the output to be lowered or reduced. So in this case attenuators are used as a variable manipulation element. Sometimes the output of the transducers may be affected due to external noise. So in this case we have to use some clippers or clampers so that we can able to process the accurate signal. So this stage is called as a signal conditioning stage. So this is the second stage of the element. Next come the data transmission stage. So in this stage it transmits the data from one stage to the another. So we are going to transfer this channel to the this is called as the intermediate stage, where the variables from the manipulation conversion to be transmitted to the next stage, that is the data presentation stage. So this through the communication to the intermediate channel we are going to transmit the signal, that is called as a transmission medium or data transmission. So final stage, this is a terminating stage. So this is called as the data presentation stage. So the data transmitted data may be used by the system that handling for the monitoring, analyzing and controlling purpose. So this is the final stage, this is the data presentation, and if the data is to be monitored, then the visual display devices. So visual display devices are used as a data presentation element, and the data to be recorded for the analysis purpose, then we can use magnetic tapes, camera and recorders as a data presentation. And for control and analysis purpose, microprocessor, computers, microcontrollers are used as a data presentation element. So these are the applications of the data presentation, and this is a terminating stage. So we comes under three stages. So first stage is a primary sensing stage, and second one is a signal or data conditioning stage, and third one is a data presentation stage. Finally the data presents we are ready for the final user or observer. So this is the final output of the thing. So if we consider some example, if we consider the ammeter, how the ammeter reads the reading, and by this and how it comes under this three stages we can see now. And if in ammeter we are going to read the current measurement, so the quantity to be measured is a current, so that is the measurement will be the current value. So primary, the moving coil acts as a primary sensing element, and the magnet and the coil together act as a data condition or signal conditioning element, and finally it is transmitted through the mechanical linkages, and which is act as a data transmission element, and finally the pointer and the scale deflects, and it is a data presentation element. So finally the moving coil will be comes under the category of sensing element, and in the data condition element the magnet and the associated components comes under the signal conditioning element, and finally the pointer scale comes under the data presentation element. Here the current that is converted into the force in the stage of manipulation stage, and the force will be deflects the pointer, and the readings will be observed in the final stage. So this is an example for the ammeter. So these are the various block. The primary sensing element means it is a sensor, and here we are using transducer as the primary element. So we already know the variable conversion element is used to convert with a suitable form, and the manipulation element that is used for the variations, that is change in manipulating the signal and convert it to the suitable range, like amplification, attenuation and clipping, etc. So the transmission is transmitted from the one form to the, it is transmitted to the another through the channel. Finally we are having the data presentation element. So this is in the form of recorder or any display device or any pointer scales. This comes under the data presentation element. So next topic we can go, that is error in instrumentation. So commonly if we have what is error? Error means it is defined as the measurement of deviation, maximum deviation so from the true value. So that is difference between the true value and the actual value is called the error. So how can we define this error? So it has three types. So that comes under the three categories. One is gross error, and next is random error, and next is systematic error. So what is gross error? The gross error occurs mainly due to the human carelessness. That is, human himself takes a reading in careless manner. So that is, if for example a person taking the reading for a measurement of 28 is the actual value, and he himself take the reading as 23 due to the poor sight, then it is due to this error is called as the gross error. So this category basically takes into the account of human oversight and other mistakes while reading. So most common human errors comes under the measurement error. So that is, for example, 28, how to measure the reading of 28 and he unknowingly taking as 23 means this error comes under gross error. So in order to reduce this gross error, we have to follow the two ways. That is, he have to repeatedly should take the reading, and in each reading he or she should take the mean value as a value. So if we take the reading repeatedly, we can able to reduce this gross error. So next category is random error. So the random errors are those errors which occur irregularly and it is called as a random, and this is mainly caused due to the fluctuations in the experimental conditions. So here we are taking some example, the unpredictable fluctuations in any temperature or voltage supply or due to the mechanical vibrations of the experimental setup. So due to this some errors are occurring, that error is called as random errors. So another thing you can take, for example, when the same person repeats the same observation, he may likely to get different readings every time. So for a set of reading, he or she getting the reading different for every time is, that's the thing, he makes a random error. Next is systematic error. Systematic error has the other three categories: environmental error, observation error and instrumental error. So what is environmental error? This type of error arises in the instrument due to the effect of external conditions on the measurement. So for example, the external condition may be due to the temperature or humidity or anything. So this temperature, if the temperature difference or temperature variation, it creates inaccurate in the reading or this causes error in the measurement means this is called the environmental error. So here we consider the example, if you measure the temperature under the armpits and during the measurement, when there is a electricity shutdown or the room get overheated, so it couldn't make the temperature accurately because of the room temperature variations. So if that variations causes the reading to get affected, then it is called as a environmental error. That mainly comes under the temperature, humidity, all comes under this environmental error. So next is observational error. So these errors are due to the lack of apparatus setting or due to the carelessness in observation or any improper setting. So this comes under the observational error. Mainly this wrong record readings or anything, it falls into the category of parallel error. We call it as a parallel error. Then instrumental errors. So these errors are arise due to the faulty construction and the calibration of measuring instrument. So this mainly due to the fault construction of the instrument. So that we get the error. This instrument is called the instrumental error. So the zero error here, the zero error is the most common type of error. It is mostly because of the it will commonly happen in many welding calipers and screw gauge. We can see this type of zero error. Next is the characteristics of an instrument. So if you see the characteristics of an instrument, we can categorize as statically and dynamically characteristic. So what is statically characteristics means? So in static characteristics, it is defined as an instrument which measure the quantity which do not vary with time or is slowly vary with time. That's considered as static characteristics. So what is dynamic characteristics? The dynamic characteristics is an instrument which measure the quantities will vary with respect to time. That is called as dynamic characteristics. Static means it does not vary with time or slowly vary with time. Dynamic characteristics means it varies with the instrument or to be measured varies with time is called as dynamic characteristics. So we can see the various characteristics of static and dynamic characteristics. So first is accuracy. So accuracy is the degree of closeness with which instrument reading approaches the actual value of the quantity. So the closeness of the value is called as the accuracy. And next characteristic is the sensitivity. What is sensitivity? Sensitivity denotes the smallest changes in the measured variable to which the instrument responds. So it is defined as a ratio of changes in the output of the instrument to a change in the value of quantity to be measured. So that is called as the sensitivity of instrument. Next is repeatability. And next is reproducibility. So it is the degree of closeness with which a given value may be repeatedly measured. That is called as the reproducibility. And drift. So the drift is the gradual shift of the instrument indication over an extended period during which the value of input variable does not change. So this is called zero drift. And the zero drift is defined as a deviation in the instrument output with time from its zero value when the variable to be measured is constant. So this is called as a zero drift. And what is meant by error? Error is the maximum deviation from the true value. So that is the static error is defined as the difference between the true value and the actual value. So the deviation from the actual value, that is true value, deviation from the true value is called as the static error. And next is the dead zone. So dead zone, and it is in some instrument it is possible that till the input increases beyond the certain value, the output does not change. So for a certain range of input values, there is no change. There will be no change in the output. So this range of input that is called as does not respond. The range is called as a dead zone. So next is threshold. So threshold is the maximum allowable error in the measurement is specified in terms of some value which is called the threshold. And next this comes under fidelity. This all comes under the dynamic characteristics. So we can see one by one. So accuracy already we saw that, sensitivity we saw that, reproducibility and precision. So drift, static error, dead zone. So resolution. So next we can see the resolution. So resolution is the smallest quantity that can be detected with certainty by an instrument being measured is called the resolution. So if a non-zero input quantity is raised slowly, the output will not rise until some minimum change in the input are done. So this minimum change causes the change in output to be termed. That is called as resolution. So next is dynamic characteristics of instrument. So in the dynamic characteristics of instrument, so some of the dynamic characteristics of instruments are dynamic error, response, speed, fidelity, and lag. In the lag we can consider reduction lag and time delay lag. So we can see here. So first is dynamic error. So dynamic error, that is a variation between the true true value of measured quantity to the values indicated by the measuring instrument which are affected by operating conditions. That is, it is a error. That is, here we are, it is considered by varying with time. That is called as dynamic error. So next quantity is the response speed. So the speed is defined as the rapidity of the instrument or how quick the instrument responds to the changes in the measuring variable. That is called as the response speed. So next is fidelity. So the fidelity is defined as a degree to which a measuring instrument reproduces a change in input faithfully without any dynamic error. That is, it produces output as like that of input. So that is called as fidelity. And lag, it is a time delay in which the system takes some time to respond. So under this comes under two categories, retardation lag and time delay lag. So in retardation lag, the response of the measurement begins immediately after the change in the measured quantity has occurred. So in this case, the response of the system begins immediately after a change in the variable has occurred. So though it takes some time to reach the final value. So what is time delay lag? So time delay. So in this case, after the application of input, the response of the measurement system begins with some dead time. So in this case, the response begins after some time delay. That is called the dead time after the application of the input. So such a delay shifts the response along some time axis and hence causes the dynamic error. So next, we can see the essential requirement of the indicating instrument. So what are the requirements of the instrument? So indicating instrument is used in electrical and electronic systems that to measure and display the quantities like current, voltage, power, etc. So this comes under electrical measurement. So for ensure the reliable performance, these instruments must satisfy the following essential requirement. So the effect of unknown quantity that will be converted to the mechanical force, so which is transmitted to the pointer which moves over a calibrated scale. So that will be attached to the pivoted spindle. So now for a satisfactory operation of the requirements, there will be three torques. That is, first is deflecting system that produces in the deflecting torque, and second is a controlling system that producing the controlling torque, and third one damping system that producing the damping torque. So in deflecting torque, so this is a torque that causes the pointer of the instrument to move from its zero position and give a reading. So for every instrument, the deflection torque is provided, and it will be provided in some various way, and you can see one by one. So because the initial thing, the current from the coil is converted to the force, so the force will tends to move the pointer, and the pointer will move from the zero position due to the deflecting torque. That torque is called as a deflecting torque. So it is produced by the measurement. Example, current or voltage that will produce a force. That force will deflect the pointer from zero. So the deflecting system converts the measured quantity into the mechanical movement. So the deflecting torque can be produced by several methods depending on the type of instrument. So first is we have many methods to produce the deflecting torque. We can see the various methods. So first is the magnetic effect. So that is electromagnetic effect. This we can found it this is a moving coil method, and it is used in a permanent magnet moving coil instrument. So PMMC instrument. Here, when a current carrying conductor is placed in a magnetic field, it experiences a force, which force tends to move the pointer from the over a calibrated scale from zero position. So this effect is called a magnetic effect. So here, the torque will be directly proportional to the current. So that is, the coil will be placed in a magnetic field. The current carrying conductor will be placed in a magnetic field, which experiences a force. That is the torque. It moves the pointer to the from zero position. So that is called a deflecting torque. So first method is a magnetic method. Second effect is a thermal effect. So here we consider two categories. One is moving coil, and it is another thing is aerodynamic type. So that is moving ion instruments. So dynamometer type instruments. So next is thermal method. In thermal method, we are using example as thermocouple. So here in which way the torque is produced means when two dissimilar metals are connected end to end and it forms as a closed loop. So in this case, when two dissimilar metals are connected from end to end, it forms a closed loop and the two junctions are maintained at a different temperature. So it will maintain then what happens, EMF will be induced, so which causes the flow of current in it. So current flow will be happen in the closed loop. As it is a closed loop, the current will be flowing through it. So this effect is called as a thermal effect. So current heats the wire and the expansion happens, and due to this mechanical deflection takes place. So for example, we are using the thermocouple. For thermocouple instruments, we are using this method to produce the deflecting torque. So next is the electrostatic method. So here, what is electrostatic means? When two plates are charged and are separated by some distance, and there will be a force exerted between them, which happens to move one of the plate. So this is called an electrostatic force or electrostatic effect. So example is electrostatic voltmeter. So based on the force between the charged particles, it will be one of the plate will be moving. So that the moving coil point will be attached to this so that the point will deflect. So that is the deflecting torque happens. Next is by induction method. So it is used in commonly induction type energy meters. So in a closed path is provided, there will be a flow of current in the disc, and due to the interaction between the induced current and the alternating magnetic field, there will be a cause of current which will cause the disc to move it. So that will happen in the energy meter. A rotating magnetic field that will induce a eddy current, that will create a eddy current, and which moves the plate and producing the torque. So this is called induction method. So next is Hall effect. So Hall sensors that produces a voltage and which will be the proportional to the magnetic field strength. So it depends upon the current. It is used in a digital indicating instrument. So current flow through the thin strip of metal or semiconductor is called as a Hall element. So when a magnetic field is applied perpendicular to the field, then it takes a charge carriers and it induces some voltage. So that is called as a Hall voltage. So the output voltage will be proportional to how the strength of the magnetic field. So that effect will be called as a Hall effect. So first is deflecting torque and second is a controlling system that produces in a controlling torque. So what is controlling torque? It opposes the deflecting torque and helps the pointer to settle at a definite position. So also it also have the another thing. It also wants to need to bring the pointer back to the zero when the measured quantity is removed. Okay, so that can be the main function of controlling system it will be producing the force that will be equal and opposite to the deflecting force. So in order to make the pointer to comes under the definite position. Okay, and also if the measured quantity is removed, then the pointer should comes back to the zero position. So this can be made through by controlling system. So we can be achieved this by two controlling methods. One is spring control and another is a gravity control method. So what is spring control? Is here a spring will be provided for restoring the force and proportional to the deflection. So here in next control is a gravity control. It uses the weight of the control mechanism to oppose the deflection. So by this two way we are achieving this controlling torque. So we can see one by one. So what is spring control? So in spring control method of indicating instrument, we should have the spring control should have the spring should have the four properties. That is the spring should be of non-magnetic. First property is the spring should be non-magnetic, and second property it should free from mechanical stress. Then third thing, it should have the low resistance property, and fourth one, it should have low temperature coefficient. So the property, it should have the four properties to meet this controlling method. So here in this spring control methods, we are using the spring attached to the moving system of the instrument. So when the pointer moves, the spring is twisted in the opposite direction. The twist of the spring produces the restoring torque and is directly proportional to the angle of the deflection of moving systems. So when the controlling and deflecting torque are equal to each other, so the pointer then comes under rest position. So the pointer will be in a particular definite position. So by this way the spring is adjusted. So this is a spring control. If you see this diagram, here we are using the two hair springs. So two hair springs are attached to the moving system and which exerts the controlling torque. So this produces the controlling torque. So that the spring should have the following. It should meet the following properties, like it should be non-magnetic and it is free from mechanical stress and low resistance, and it should have low temperature coefficient. So here this is a spindle. We are attached in this. We have attached the pointer, and also the springs are attached. Two hair springs are attached to this spindle, which is pivoted at the edges, and the pointer is attached to the scale. So here the springs are made up of non-magnetic materials. So the non-magnetic materials are silicon, bronze, phosphor bronze, and German silver, etc. So most commonly phosphor bronze are preferred. Here the inner ends of the spring is attached to the spindle. So the inner end is attached to the spindle and the outer end is attached to the lever or any arm. So that is attached to the set of screw that will be mounted on the front of the instrument, so that we can able to make the zero adjustment easily. So the spring will be attached to the screw actuated in front of the instrument, so that by the adjusting that we can also able to adjust the zero adjustment also can be done here. So what happens, how it is controlling when the pointer deflects from the zero position and it should be at a stable position, the spring will be here the spindle also attached to this spring. So if it is moving, the spring will be get tightening and it will be keep the position at a controlling one, and when the deflection or measured quantity is removed, then the spring will be loosened and it will be come back. It will make the pointer to the zero position. So for a flat spiral spring, the controlling torque developed by the deflection will be, the controlling torque will be Tc is equal to K into theta. So we are deriving the spring from the, if we deriving the torque for the, by using the spring stiffness and strain, means we will be getting the torque equation as Tc will be directly proportional to angle of the deflection. So here the K will be the spring constant, and we know the spring should have the following four properties, that is it should be non-magnetic, it should be free from mechanical stress, and it should be have low resistance and low temperature coefficient, etc. So if we see this, the deflection means, so if we equate the controlling torque for the controlling nature, the torque at equilibrium condition, controlling torque will be equal to the deflecting torque. So deflecting torque will be proportional to the operating current. So if we equate both the condition, means deflecting torque and controlling torque will be equal. If both the things are equal, what will be the relation? So that is theta I will be directly proportional to the theta. So that is we will get the relation of I will be directly proportional to theta. So when the current is removed due to the spring force, the point will come back to the initial position. So it is this condition is used in all indicating instruments. So what are the advantages and disadvantages of spring control? So it is cheap. The control is independent of temperature variation, and it does not deteriorate with time. So it does not change with time. So this is the advantages of the spring control. And what is the disadvantage? This type of control can be used only in vertical mounted instruments. So this is the spring control, and next comes under the gravity control. So in gravity control, so this is a diagram. So if you see the diagram of gravity control, here we are using the two control weight. So here this is a pointer and we are fixed to the arm, and here we are attaching the balance weight and the control weight. So here the control, by using the gravity, this control, we could able to control the controlling the instrument here. So this control is done by gravitational force. So in this type of control, a small weight is placed in the arm attached to the moving system, and the we can able to change the position or change. We can able to change the weight so that we can able to adjust it. And initially, when the from this system, you can see here this diagram. Initially, this diagram we are considering. So initially, when the pointer is at 0 position, so this is 0 position. And the control weight will be in the position 1. So you consider this is a 0 and this is the position 1 and this is the position 2. So if initially the pointer will be at the 0 position. So here now when this is in a 0 position, there will be no controlling torque. When the pointer deflect, now when deflection happens and when the pointer deflects to some angle theta, so there will be some deflections. Here due to gravitational force, there will be some deflection. Okay, so it comes. So the point now here deflects through an angle theta, and it comes to the position 2. So from the position 1, it comes to the position 2 by angle theta. Suppose if the point deflects through an angle theta, then the control weight also will move to the point 2 and making an angle theta. So the control weight now acts as from the distance L. We are considering from the center point. We are considering this length. Now, in this case, the component of the weight will try to make the balance. So here the weight will be acting towards downwards. Now it will try to control, and it comes to the position of vertical component W sin theta. So from this, if you consider the horizontal component will be the W cos theta, and the vertical component will be W sin theta. So now the pointer will try to control and will come back to the vertical component W sin theta. So what will be the force? Then force will be acting, that force will be called as gravitational force, that will be of W into sin theta, that is the force. Now if you, what is the torque? Torque means we are considering the force into the length. Then if you considering, we will be getting WL sin theta. So if you equate the equilibrium, so at equilibrium condition, the controlling torque will be equal to the deflecting torque. So if we see, if we equating means we will be getting that I will be directly proportional to sin theta. Here the deflection of here the current is based upon will be proportional to the sine of the theta. So what is the thing here? In the gravity control, there will be non-uniform. Here will be this case there is non-linear. So the scale will be designed non-linear. So this is the drawback in the gravity control. And another drawback, it should be vertically. The instrument should be mounted vertically because the control weight is acting towards downwards in a vertical position. So in the gravity control, the instrument should be positioned vertically. So that this is also one of the drawback. And next thing, it is non-uniform. It is the non-uniform scale because I will be directly proportional to sin theta in this case. So in this case, it reveals that this equation will reveals that it will be the non-linear scale. So it indicates that it will be a non-linear scale. So this is the torque. I tell you that TC torque, controlling torque will be W sin theta into L. So WL sin theta means WL is constant to kg sin theta. So this is the controlling torque. Controlling torque is equal to kg sin theta. So if we equate this with the at equilibrium position, if I equate the controlling torque and the deflecting torque, then I will be proportional to the sin theta. The scale is non-linear and it will increase the weight of the instrument, and the instrument needs to be in a vertical position. So the instrument to be kept in a vertical position. So next is a damping torque. So what is damping torque? Damping torque makes the pointer to return to the zero position gradually after the measurement. So it minimizes the oscillations of the pointer. So it is provided in order to bring the pointer to rest within a short period. So here we have three types of damping case. So one is a under damping, and next is a critically damping, and another one is a over damping. When the moving system oscillates about the final steady position with the decreasing amplitude, and it takes some time to come to rest. So that is called as a under damping one. and when the moving system moves rapidly but smoothly to its final steady state position, it's called as a critically damped. And another thing is a over damped. Here when the instrument is over damped, the moving system moves slowly to its final steady state, so that is called as over damped. So there are 3 types of damping method, and if there is no damping torque, the pointer will, what happens when there is no damping torque means, if there is no damping torque, then the pointer will keep on moving to its final deflected position for some time before coming to rest. So this happens due to the inertia. So due to the inertia, it will not come to the rest position. So in order to prevent from oscillations, damping torque is necessary. The damping torque can be of following methods: air friction damping, eddy current damping, and also there is a fluid friction damping. So it also same as that of air friction only. So we can see this one by one. And this is the air friction damping. So in this air friction damping, so here the point is attached to, other end is attached to the piston, and it is connected in the lightweight piston. Okay, that will be light aluminum piston, and that is attached to the moving system. This pointer, this moving system I am attaching to the pointer. The piston moves in a fixed air chamber. Here it is to be closed at one end, and the chamber wall should be of uniform and very small. Okay, consider the chamber to be uniform and very small. The pointer is attached to the moving system, and it makes the piston to move to and fro. So when the piston moves into the chamber towards the position 1, so here consider this is position 1 and this is position 2 means, but if piston moves towards this, what happened, there will be air inside the chamber will be compressed, so and build up the air pressure, and which opposes the motion of the piston. Thus the motion of the pointer also will be damped. So when the piston moves out of the air chamber, towards the next position 2, the air pressure near the position 1 will drop, and whereas the air pressure near the position 2 increases. So this happened to and fro. So by this air we are able to damp the oscillations. So necessary damping is provided here by air friction. Same thing for a liquid friction will be, oil will be used as a for a fluid friction. In the case of a fluid friction, in case of air, oil will be filled, and the oil will be helped to provide some friction. So this provides, and maintaining the pointer will be prevent the oscillation and help for the damping process. So next is the eddy current. So eddy currents are induced in the conductor due to the change in magnetic field produced by the permanent magnet. Here the eddy currents will be induced in additional to the magnetic field. It produces the current, eddy current, by the external permanent magnet. That called as a permanent magnet is placed, and it will produce the eddy current, and it will be helpful to providing the controlling the pointer oscillations. So this damping is used in the permanent magnet moving coils, and there are 2 methods of damping produced. So this is eddy current damping. So here see permanent magnet will be placed, and here there will be how the damping force will be evolved. So we are placing the metal former, and it will be placed in the magnetic field. This method implies this coil is bound on a metal former made of aluminum, and which the eddy current will be produced on the coil, which moves in the permanent magnetic field. So this is the eddy current damping. And next one is this method. In this method, if you see the spindle, the pointer will be attached to the aluminum disc. So this is spindle, and it is attached to the moving system, and here there is a aluminum disc. So there will be some operating current. So this will makes the pointer to deflect at some angle. And if here we are placing the permanent magnet north and south, the magnetic field will be producing, and the disc here will be rotating based on the deflection, based on the current. So that disc will be moving and makes the pointer to move. And if the disc rotates under the influence of the magnetic field north to south, what happens? Here it will produce some EMF. So what happens? This EMF will again induce current in the disc. So what happens? Lenz law, by Lenz law, it will produces the opposition force to that of the main force. So what happens? There will be opposition which makes the pointer to damp so that the oscillation can be prevented. So this method is called as the eddy current method, and this method is most commonly preferred and it is the most efficient one. So this is the necessary requirement of a instrument. So that is 3 cases we have saw, that is deflecting torque, controlling torque and damping torque. So these 3 torques are efficient or essential for the instrument to perform in a smooth manner. Thank you. So this topic we can end our section. Thank you.